Next, we have Dr. Franklin Moore. He's a professor of civil engineering at Rutgers University and an affiliated member of the Center for Advanced Infrastructure and Transportation. His research focuses on the development and application of technologies to diagnose, preserve, and renew civil infrastructure systems.
I decided to try to expand this to 3 demos of technologies. 2 you may have heard of. Obviously, the BEAST will be the primary one. We start with just some brief introductions, overviews of where these technologies come from, what they can do, and then when we get out there, you'll be able to see them sort of firsthand. So the first one that's been under development for probably about 5 or 6 years is focused on problems with load rating. And generally what we're focused on are specifically the bridges that cannot be effectively load rated with the standard single line girder approach. Obviously the majority of bridges fit in very nicely with that. There's a group of bridges that don't. And so we are focused on how can we collect data, calibrate models, and perform refined load ratings in a fraction of the time that you can do it with sort of conventional tools. And what we came up with is something we call THMPR. We shoehorned it in a little bit, but it stands for Targeted Hits for Modal Parameter Estimation and Rating. And basically what it does is it's a reconfigured pavement falling weight deflectometer. I don't know if you're familiar with those, but it delivers a relatively large impact of around 30,000 pounds, focused below about 50 hertz, to a bridge, and it induces free vibration. It then has a series of sensors that measures that vibration, and then we rove this around the surface of the bridge, stitch it together, and we can capture the dynamic signature, frequencies, mode shapes of the bridge, which are related to how the stiffness and mass are distributed through the structure. And so I'll give you a quick video here of it. So you pull it out onto the bridge, and we do have a little mock-up bridge over in Livingston, and so you'll be able to feel the impact. The reason we do a large impact is if we didn't, we would have to close all the lanes of the bridge. But because we can overwhelm traffic, we can actually leave certain lanes of the bridge open and do the impact testing with just a single lane closure or slowdown. And so we're pressing a load plate against the surface of the bridge. It's got a series of load cells, and then we have this impact carriage that gets dropped. As it bounces, we chase it with 2 pneumatic actuators and catch it. So we get a big single impact, and you get a free vibration response. The response lasts for about between 3 and 5 seconds, depending on the bridge, and we can get upwards of 2 G locally. So it is a significant impact. The force levels are relatively low, though. You're thinking about rear carriage of a tractor trailer sort of load, 30 kips. But because it's dynamically, we get a very good signal, so we can overcome all of the ambient vibration. And if we're going to compare this to what is typically done, again, this is for situations where you've got to perhaps do some load testing to figure out how the structure might distribute load. There's some uncertain mechanisms there. So you can, I sort of broke these apart into quasi-static. So think of strain gauges, displacement gauges, trucks or operating traffic in terms of prep time, testing time, reporting time, and then dynamic, right, where you can go out there and either just monitor it under traffic. You can also do multiple input, multiple output testing either with shakers or impact devices. But because we tried to package this in a way that can be applied very quickly, we're actually down to, when things go really smoothly, we're down to about 30 minutes per span. So in terms of collecting the data, that then feeds into a refined model to perform the rating, right? So it's completely consistent with the AASHTO MBE. We're not doing anything funny. All we're doing is building a model and calibrating that model with this information we're getting from the bridge. And if there are certain mechanisms that you don't want to include, like a frozen bearing, we simply cancel it out and produce the rating, assuming that that frozen bearing is no longer frozen. Right? So that was the first one. The second one has probably gotten a lot more attention than most of the other things we've been doing around here, and that is what we call the RABIT, the Robotic Assisted Bridge Inspection Tool. You may have heard of it. This is what it looks like. In some ways, it's similar to THMPR in that the technologies that are on here are well developed. The innovation here is packaging them together so that we can collect the data relatively quickly compared to the historic sort of manual approaches. And the RABIT will be out there today as well, so you'll be able to see it driving around. But it does GPR, electrical resistivity, impact echo, ultrasonic surface waves, and it also does high definition imaging, so we can do automated crack mapping. But you can see it operating, so it's taking a lot of this data simultaneously. It does have to stop for certain types of data, like, for example, the impact echo. And so the time it takes to scan the bridge has a lot to do with how often you want it to stop. The standard that we generally use is about 2 feet. So if you stop and take data every 2 feet, that will, I think we can do about 3,000 square feet per hour of bridge deck. And to give you an idea of what some of these things look like, this was a bridge that has been decommissioned, but it was located outside of DC in Haymarket, Virginia, and it was scanned in 2009, 11, 14, and 15. And you can clearly see these are, I think this is impact echo. So what you're looking at here, more or less, are the growth of delaminations. The red being some significant delaminations that you can see between 2009 and 2015 were growing. So there was things happening under the surface. The bridge was decommissioned shortly after this, but I can tell you from 1992 until 2015, when it was decommissioned, the deck was a 6. Right? So the visual inspection, it's not the inspector's fault. They simply can't see what's going on under the surface. And so one of the applications here, we can talk more about it in Livingston, would be maybe prior to repairs to get really good quantities of how much actually needs to get repaired, or to make decisions, is a repair possible or a replacement. Okay, so now what was advertised, which is what we call the Bridge Experimental, or it should be Evaluation and Accelerated Structural Testing Laboratory. We spent a lot of money here at Rutgers coming up with acronyms. So that's the BEAST Laboratory. The vision for this, and you guys are not going to believe what I'm about to say, but one of the problems is that bridges do not deteriorate fast enough. And because of that, if we're waiting 10 to 20 years to see deterioration, if I make a change today, it takes me a very long time for me to know what is the impact of that change and how much is it worth doing it differently versus doing this the way it's always been done. Because of that long feedback loop, things have to necessarily move very slowly. And so, sort of to put a point on this, if we look at some other technologies, if we go back 10 years and look at what cell phones looked like, I was shocked, by the way, when I looked this up. iPhone was not the top smartphone in 2007. It's amazing. We were still playing around with these little keyboards. And if you go back 20 years, right, the big breakthrough was an internal antenna. And by the way, 20 years ago, phones were actually phones, right? Almost nobody uses a phone as a phone anymore, right? It's an email device or text messaging or web browser, whatever it is, camera. So if you look at how fast technology can move and how this long feedback loop is not allowing us to take advantage of that. We're talking here about some information technologies, but there has been explosions in materials technologies over the last 20 years. And it's very difficult to understand what is worth investing into and what is not. And so the idea here was if we could do something to try to shrink this feedback loop, that we could make a positive impact on the bridge engineering profession. And so what we came up with was this accelerated testing lab. And this is what it looks like. Well, this is sort of what it looked like under construction. You guys will see what it looks like today. But it can accommodate full-scale superstructures, and I'll say relatively full-scale. 50-foot span by 28-foot width. So there are clearly bridges out there that are that size. We could potentially also do half-scale bridges that would simulate something more like a 100-foot span, which is more of a nominal bridge span. But we're relatively full scale. It is a very large environmental chamber, right? And so we can control the temperature swings, freeze-thaw cycles, et cetera. So we can get it down to 0 degrees Fahrenheit. In fact, I had it down to -5. We held a workshop, and I thought, boy, this would be a great idea. Let's turn it down to -5. And it was a terrible idea because that is really cold. You know, it's one thing to put it up on the scene. It's another to walk in there and your ears hurt immediately. I mean, it's pretty impressive. So we can do down to about 0 up to 104. So we can do a bunch of different freeze-thaw cycles. We have a system that can apply de-icing chemicals. We can go up to 18% brine. And we have a rolling live load. So it's basically the rear carriage of a tractor trailer, and you'll see this rolling back and forth. Moves at about 20 miles an hour. We can do about 17,500 cycles a day, and we can apply up to 60,000 pounds. So if you're thinking about a standard design truck, this is roughly double the weight of a rear carriage, or about 20% more than the tandem load. All right, so this is the idea of it. It's a big pit in the ground. Eventually, the first specimen will be built on site probably this fall, but in the future we can build them off site and have them cure and pick them up and drop them into the pit, as you see here. And then everything is on rails. So we've got a series of environmental enclosures that can slide closed, and then we have the beam that carries the live load carriage. That can be located at any location along the width. So we're going to be roving the live load. So we're not just loading one section of the bridge. But this then gets enclosed. This animation is a little old. We're not applying water or precipitation in that way. But you can see we will be providing precipitation. The carriage is actually on a winch system, so it gets pulled back and forth across the bridge. It has speed up and slow down ramps, so on the bridge itself it's always a 20 mile an hour constant speed. We can go slower, but then you can sort of heat, cool, and push this through a lot of loading cycles, and then eventually we're going to get some deterioration, and then we can have all of our other tools that come out and begin to track from a very early age. We're thinking of doing full NDE scans roughly every 7 days, so that we can see how deterioration begins and how does it progress, right? So we can help with some of the deterioration models. Those are what we would call longitudinal studies, trying to forecast how things will change in time. And we can also do a series of comparative studies. So we can look at two competing systems, right? Whether it's reinforcement coating or different sealants or overlays or cover thicknesses, whatever you want. We could look at incorporating both of these on the same specimen and then simply documenting how they perform. Right? So the potential focuses of what I'll call primary objectives. We have some secondary objectives which aren't going to affect the specimen and things, and those are maybe of more academic interest. We also have something I'll call payload projects that are things like, what are the durability of sensing systems? A lot of vendors for sensors constantly get asked that question. We could examine that here. But what you're probably interested in primarily are these primary objectives. And so the first set would be performance of specific components. So here you have in the longitudinal studies, we could estimate deterioration curves for certain types of bridge decks, steel coatings, joints, bearings. In fact, the first specimen we're thinking we'll have 4 steel girders. We're probably going to use a couple different types of metallizing, a galvanized, and then a standard paint system, and do a comparison of how those perform. We can also do all of these comparative studies, different rebar coatings, galvanized, epoxy, black steel if we wanted to do a better job of calibrating some of the deterioration curves. We can look at different repair techniques, right? So on the longitudinal study, again, we're just tracking that with time and trying to get a calibration for how much of 1 month in the beast corresponds to what time out in real life. Of course, that depends on where real life is, right? If it's in Arizona, that's very different than if it's in New Jersey or Pennsylvania. We can do comparative studies, all the different types of overlays, for example, or when should they be applied? I mean, that's one of the big questions. What should I do and when should I do it? And so we could examine both of those, and then we can also look at certain maintenance and preservation activities in sort of a controlled manner. So with that, I don't know how long I took, but if there are any questions, you know, it's probably a little bit easier to talk as a group here when we're out on site, particularly when this is running. It's a little bit loud.
I forgot the name of the other equipment that you had, but it tracks vibration, I believe. Could that refine distribution factors, for example, between girders?
Actually, that's pretty much the primary role. That was our, you know, as you know, the distribution factors are probably the primary influence on where that rating goes. And that relates to a lot of, you know, how those girders are actually sharing load. The code necessarily makes a lot of simplifying assumptions. And so generally when you go out and take some measurements, one of the biggest sort of bang for your buck in terms of an increased rating comes exactly from that, the distribution factors. So yes.
One of the experiences that we've had, and Julia probably comment on this as well, is deck slab bridges, where the distribution factors for live load is per AASHTO is not quite refined. Is that something that that equipment can probably?
Yeah, I mean, in those cases, I would almost say we might want to forego distribution factors, just perform a refined load rating. I mean, in some ways, if you look at a slab bridge, sort of the concept of a distribution factor breaks down a little bit because, you know, I know we have these old, okay, you know, 1 foot width strip type thing, but that's not how it really performs. I mean, a slab is really a two-way system. As much as we want to try to make it a one-way system, the stiffnesses in both directions are very comparable. So in those cases, you know, this system could work well, but I guess we could back out an equivalent distribution factor, so the single line girder approach would give you the same rating as the refined method. But, you know, for bridges like that, for arch bridges, you know, some of these lend themselves much better to refined, you know, more 2- or 3-dimensional models than the single line girder. But,
Thank you.
but that's Thumper, by the way. We try to name things after Disney characters. So.
Any other questions?
All right, just like one of my classes. No questions. Everybody's sleeping.
All right, thank you, Dr.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.